We are in the process of launching Google University, we have various mottos, including never stop learning, innovative education for Googlers, and my personal favorite, which is don't be stupid. And over the course of the summer, we're having a series of inaugural lectures on topics that are related to Google in one way or another. And I was delighted to be able to invite Mehran Sahami as our first speaker. Mehran, many of you probably already know, perhaps most of you, as a Google senior research scientist. He's taken on additional responsibilities of being an associate professor and associate chair for education in the computer science department at Stanford, where he is leading I think a fairly radical rethinking of the computer science curriculum. So a great way to start off this lecture series is by somebody who's famous both here and up the street. And I'd like to welcome Mehran back. Thank you.
Thanks very much. Thanks for coming. I'll hopefully try to keep you awake this afternoon after lunch by talking to you a little bit about the frontiers of computer science education, how we expand them, and show you some fairly eye-opening statistics. Some of you may already be familiar with what's going on in computer science education. But for those of you who are not, let me just show you what many consider the most famous chart in computer science education. And what this is this came from the Higher Education Research Institute at UCLA. What they do is, on a fairly regular basis, they poll high school students to determine what areas they're interested in going into. And what this chart shows is the percentage of freshmen, the incoming freshmen to college, that are intending to major in computer science. And as you can see from that graph, broken out by men, the overall total, and women, back in 1999, life was good. Right? Everyone and their dog wanted to be a computer science major. The dot-com boom was happening. We got a huge surge in the percentage of students who said they were interested in computer science. And since that time, this graph only goes down to 2004. We've come down pretty drastically. As a matter of fact, in terms of percentage of women, we're at a historical all-time low with respect to how long this statistic's actually been measured. Right? We're less than 0.5% now of incoming college freshmen, women, are actually interested in going into computer science. Now, if we take a look at what this has actually translated into, right? So you might say, well, this is student interest coming into computer science. Let's spend a little bit of time thinking about where we're going to go from these numbers we're seeing right now with interest in terms of how that translates into the computer science student pipeline, looking at colleges and also looking at some other leading indicators in high school to see what is going on with students interested in computer science. From there, we'll spend a little bit of time talking about misperceptions of the field. What are some of the factors that are affecting students' choices and what the reality is behind the choices that they're actually making. And then I'll spend some time going from that leading into the curriculum revision we're doing at Stanford, which is, as Peter mentioned, a pretty significant revision in terms of our computer science curriculum. I'll tell you about the structure of the curriculum, especially if you're a Stanford alum. You'll see a lot of things that are different, some of the issues we faced in doing it, and the broader context of trying to situate some of these changes in terms of a larger community of people that are dealing with some similar issues. And then lastly, talk a little bit about broadening the initiative to think about ways we can think about life beyond Stanford to have an even larger impact. So to start off with the computer science student pipeline, that previous graph I showed you the interest of incoming college freshmen in computer science. This is in terms of when students actually get to college, what percentage of them actually, or what number of them actually end up majoring in computer science. So this is the number of declarations in computer science. And you can see it follows that same curve. So we had a peak in 2000 around the time of the height of the dot-com bubble, and the numbers have fallen pretty drastically. In terms of absolute numbers, the number of students going into computer science is roughly 50% of the peak back in 2000. Another thing that's interesting about this graph is there's actually two lines on it. The top number is the total number of students going into computer science. The bottom number is the median number of students per department. And if you think about that, you might say, well, that's kind of an interesting phenomenon, Mehran, because the median number of students per department is actually going up, while the number of students is remaining constant. Right? And if you put those two bits of data together, it tells you something. What does it tell you? There's fewer computer science departments. There are actually schools that are shutting down their computer science department. These are non-trivial schools. So Tulane, anyone graduate from Tulane? Their computer science department no longer exists. And if you're wondering, who may have graduated from that computer science department, David Filo, one of the founders of Yahoo, actually graduated from that department. It no longer is there. As a matter of fact, they shut down most of their School of Engineering except for one or two programs. And so this number is pretty significant, right? The 50% drop that we're seeing here is nationwide. And if you think about that, there are some schools that have what we refer to as control flow. So Carnegie Mellon, for example. Any Carnegie Mellon grads here? No one. That's surprising. Very surprising. Carnegie Mellon actually has control flow, which means they have the same number of students coming into their program. It's just a different number of students that are actually applying to their program at a given rate, right? Which means that if there are some schools that, despite this drop, actually have the same number of students, this drop is disproportionately larger at other schools. So when I talk to some friends at other schools, for example, that will remain nameless, they give me numbers like we had an enrollment drop of 80% or 85% or 90%. All right, so there are non-trivial drops in enrollment that are happening. Now, how did this translate to Stanford? Right? So if we bring it back to Stanford for a moment, here is the last 15 years of data of the number of CS majors we've had. And you take a look at this graph, and you see it follows roughly the same shape of the number of students intending to go into computer science. We had a little uptick recently. But you stare at this graph long enough, and you think, you know, there's another graph I've seen that looks something like this. And then you think for a while, here's a slightly more well-known graph. Here's the NASDAQ Composite Index, averaged on an annual basis over the same period of time. And so you see this graph and you see the other graph, right? And sort of that inner data analyst in you comes out and says, what happens if I put these on top of each other? Okay? So I'm not only putting them on top of each other, but students are not a market in the same way that the NASDAQ is, right? It takes, if NASDAQ fluctuates, it takes some time for that information to get into students' decision-making process. So what I'm going to do is I'm going to shift the declaration period to align it, the academic year, to align it sort of backward in time with the calendar year, and normalize these graphs by their 1998 values and then put them on top of each other, right? And what you see is if I take the entire period, a very strong correlation, 0.61, right? And they have the peak in the same place. They sort of have the same growth ramp, the same decline, except for one interesting point that you look at. And you look at that graph and you say, well, something's going on sort of later on in that graph around 2003. And the natural question to ask is, what happened in 2003? And you start to look around. You need to dig a little bit more than just what happened at universities in 2003, because there wasn't a lot of stuff in particular that happened with respect to curriculum at universities in 2003. What was happening was something external. And that external was, it was in this time period that all this news started coming out about job offshoring, and that there weren't going to be jobs in computer science anymore because all the jobs were going overseas. So even if the economy seemingly was recovering with the NASDAQ coming back up, that wasn't necessarily going to translate into jobs for computer science graduates. And so as a result, that information in some form or another, you could say, was internalized by students, and there continued to be a decline in enrollments. Okay? Interestingly, if you look at the correlation up to 2003, right, so you just look at this 10 years from here back, the correlation is almost 90%. Right, which is just astounding for any data that's real-world data, right? And you get 90% correlations when someone's doctoring data. But this is, pretty astounding to think of that, and then suddenly there's this sharp change that happens. Okay, so there's one possible solution, right? We just get one more bubble, right? And I actually, being at Google, I need to thank you for trying. Right, so here's a couple headlines from around the time of the Google IPO. Will Google bring back the IPO, bring back the bubble? This one I thought was particularly interesting. Google with a market cap north of $15 billion, right? This was the time of the IPO. Blows in the stench of bubble 2, right? They were just off by about an order of magnitude. But Google certainly tried, right? I mean, you could say that a lot of the economic boom that's been happening, that growth that's been happening in the NASDAQ, a lot of it came about as a result of things that were going on at Google helping to reinvigorate the market around high technology. But the bottom line is that hope is not a strategy, right? We can't hope for there to be another Google or a bunch of other Googles, or to just get so big that everyone says, I have to do computer science, right? As an educator, you can't expect the rest of the world to solve the problem for you. So what can we think about doing? Okay? And one of the other things you could actually think about is historically, if you take this graph further back in time, interestingly enough, we actually were in a second bubble. Most people don't know about this first bubble that happened back here around the time of the personal computer and hard drives and hardware that came out was kind of when this first bubble happened. But we actually were in the second bubble if you go back further in time. And you can see, again, just how bad the graph is, especially with respect to women, if you were to take it all the way back to the 70s. Okay? Uh-huh. So what I would say is, if you talk to some economists who believe that there's cyclicality, you could expect that. I'm not going to count on it, right? And I think if people really knew if there was going to be a bubble in another 15 years, the market would probably arbitrage it out. So I don't know if we can really count on that.
So my interpretation of the peak in '82 is that it didn't have so much to do with outside market forces. It had to do with the fact that computers were interesting. And if you wanted to play with one, you had to be a computer science major. And by 1984 or so, you could go out and buy one. You didn't have to use the facts in the computer science department. So I think it's a sort of a rational response to that.
That's a fantastic point, and it really leads into the point that what we need to do is make computer science interesting again. Right? We need to get what it was that was motivating these people to come into the field because it was interesting to them. We need to create that kind of excitement again around computer science. But I think you're right.
Kind of a devil's advocate question here. How bad is this actually? I mean, I can imagine that people are fleeing to like computational biology, for example, or something, and that really, Google still needs computer software engineers, but really the market as a whole doesn't, and they're going to things doing computation in other fields. Do you have any?
That's an excellent question, and you're about 10 slides ahead of me. So I'll show you some pictures about what the market actually looks like, too, and what the demand is versus the production. Okay? So if we look at some other statistics, we could say, well, what's a leading indicator, right? What is some leading indicator we can use to see what interest exists in computer science? And so one is to use the AP exam in computer science and high school AP exam. How many people took the AP exam in high school? Okay, fair number. So here is the number of students taking the computer science AP exam. There's actually two exams. There's an CSA exam, which is kind of roughly comparable to a 1 quarter or 1 semester class, and the AB exam, which is supposed to be roughly comparable to about a year of computer science. And here's those numbers, and you can see again, there's a little bit of a peak around here. The numbers decline a little bit and flatten out. Just in case you're wondering, you might have heard that the AP exam changed language. In fact, in 2004, it did change language from C++ to Java. But you can see that that didn't have a huge impact one way or another. It did have somewhat of a longer-term impact that some teachers eventually decided to stop teaching computer science in high schools because they didn't feel prepared for the language change. But that's a separate story. But you can see that these numbers sort of go up and decline a little bit. And then you could say, well, oh, sure. Sorry, I've got to remember to repeat the questions or to ask you to use a microphone to see the questions. So you might look at this and you might say, well, that's kind of interesting, but what does that really tell me? Well, it's more important to look at this in contrast to a few factors. One is that the AP exam, the CSAB exam, is actually being dropped by the College Board starting next year. So you would think computer science would be something that you would expect students to go into, and there should be a growth in computer science, and so more students should, in fact, be taking this CSAB exam going forward. But in fact, the numbers for the AB exam are going to go away. It's no longer going to be offered after this year. Okay, why would that be? Okay, and it actually is along with a few other AP exams, right? So the other ones that are also being dropped after this year are Italian, Latin literature, and French literature. And if you look at all those, you might want to come to a particular conclusion. But despite the company, you cannot consider Java a Romance language. Okay. But if you think about this relative to what's going on, you might say maybe all AP exams are suffering some kind of decline, right? In fact, no. The AP exam, for example, in calculus is extremely healthy, has been going up every year for the past decade, both the AB exam and the BC exam. And when you plot those relative to computer science, what you realize that computer science, one, pales in comparison, and two, it's not the number of students taking the AP exam. There's actually more students every year taking AP exams in general. And there's a very healthy pipeline of students that are taking technically oriented courses like calculus. They're just not choosing to go into computer science. Okay? So before we get too excited about what looked like a little bit of an uptick in 2006, 2007 for the CSAP, right, when you plot it on this kind of scale, it's basically just flat, and it's not showing nearly the kind of growth anyone else is. As a matter of fact, if we look at some other exams, so here's some places like biology and statistics, right? Statistics, its first year ended up a little bit lower than CS and just zoomed up like crazy. But these are fields that you could say have some bearing on computer science, right? Like computational biology, you could think of statistics related to artificial intelligence and machine learning. So in some sense, there are other disciplines which are somewhat CS related, which are also seeing major growth in students taking exams. Now, part of this growth in exams is just getting into college has gotten more competitive. So more students are taking more AP exams and more schools are offering AP courses. That's just part of what these graphs are also telling us. But one of the interesting things is across exams, computer science is the only exam that has actually shown a decline and stagnation over this period of time. right? So there's a bunch of different exams. If you want to go to the College Board, you can get all these stats for the last 10 years from the College Board, and it's interesting to see the computer science, which you would think is this booming field in the last 10 years, is the one that's actually suffering the most in terms of this leading indicator. Okay. So here's a sobering thought. The Studio Art AP exam. How many people knew there was an AP exam in Studio Art? Right? Did someone actually take it? Did they take it? No? Yeah, this was what I asked. Was they have AP exams in Studio Art? Yes, in fact, they do. And since 2004, more people take them than take computer science. Okay? Again, even Studio Art just showing tremendous increase. So there's really a problem here, right? The problem is not that students are deciding not to get more prepared for college and taking less AP exams. The problem is specific to computer science. Okay? So let's think a little bit about some of the misperceptions of the field which are causing some of these effects. We talked about some of the economic factors previously. Okay? So here's a little bit of a pop quiz. Right? I want you to fill in the blanks. According to the Bureau of Labor Statistics, blank write, test, and maintain detailed instructions the computers follow, and blank design, create, and modify computer applications and systems. And your two choices to fill in are computer software engineer and computer programmers. Okay? Do you think you could fill those in with certainty? So here's the interesting thing. You might say, but Mehran, why are you giving me this exercise? Why do I care about the difference between computer software engineer and computer programmers? Because if I go to the Bureau of Labor Statistics, right, it turns out that the answer is the computer programmers, for some reason, are the ones that write, test, and maintain detailed instructions the computers follow, and software engineers are the ones that do this other stuff. Okay? But if you go to the Bureau of Labor Statistics, and I'm not talking about the Bureau of Labor Statistics in the 60s, I'm talking about the 2008-2009 edition of the Occupational Handbook, right? What you see is this picture, and this description right under the picture that says computer programmers write, test, and maintain detailed instructions the computers follow, and this is a picture of someone alone by themselves in a room working with a computer without any interaction with anyone else, without any social context. While their jobs are being sent overseas, I'll show you the stats in just a second. Oh, and by the way, in case you're wondering, they're all white men who wear glasses. S-E-E-S? Oh, my bad. Thank you. Spelling mistake. Yeah. So if you read between the lines, I'll show you some more of the stats in just a second, but if you read between the lines, if programming jobs are being offshored, if that's the perception, right, and if that makes students believe that CS is less likely to lead to a job, it means that they must be equating computer science as just programming. Okay? Now, if we look at the statistics as to how that bears out, here's the truth on offshoring. So the ACM commissioned a task force in 2000, actually it was before 2006, the report came out in 2006, to find out whether or not offshoring was a significant issue. And what they found is that there's actually more IT jobs in the United States now than there were at the height of the dot-com boom. At the top of the peak in 2000, when there were all those jobs, there's actually more now. But students don't necessarily know about it. And even worse, not only do I talk to students, I talk to their parents. And their parents don't know about it. There are students who want to go into computer science, and their parents tell them, no, you shouldn't go into that field. There's no future in computer science. And you might be wondering why. Well, here's what the Bureau of Labor Statistics has to say. What's the predicted job growth from 2006 to 2016? If you're a computer programmer, remember the definition of a programmer, your prospects are below average. If you're a computer scientist or software engineer, remember the clear distinguishing factors of what a software engineer was, your prospects are well above average, right? When I showed this to the rest of the faculty in our department, they had two comments. One was, well, if I can't tell the difference between those things, how do I expect someone who's a junior or senior in high school to? Right? That's number one. And the second one was, hey, computer scientists, we must be okay, right? Because we're above average, we're computer scientists. In fact, if you go to the Bureau of Labor Statistics, this job category is called computer scientists and something else. Do you know what the something else is? Database administrators. Okay? They get lumped together in the same category. So there's certainly confusion from this bureau that's supposed to be telling us what the job outlook actually looks like, right? And what we need to do is to really create an awareness of computer science in the large, because computer science is really fundamental to other fields. It's not just programming, right? And in some sense, even if you think of computer science as programming, it's not just sitting in a room by yourself programming, but it's having a fundamental impact on other fields, and we'll see some examples of that in a bit. Okay? So getting back to John's question, is this really an issue? right? I mean, are we just, yeah, there's going to be some students trained in other areas and everything will work out. So here's annual degree production. And so this is a portion of a slide that's courtesy of Eric Roberts that many of you probably know from Stanford. And it's actually triangulating, if you want to read this whole section, sort of statistics coming from a bazillion different places. Because as you can imagine, you know, there's lies, there's damn lies, and then there's statistics. And so we try to get as much sort of statistical integrity as we can. So here's annual degree production in computer science, PhDs, master's, and bachelor's degrees. And so one question we might ask is, well, what's the demand? Here's the demand. Right? If you took every single person, this is the annual demand, every single person who's getting a PhD, master's, or bachelor's degree in computer science, including the very worst computer science major you knew. So think back to school and think about like that person who just managed to get it through, right? But you were like, oh, no way, there's no way they're going to get hired by anyone. All of them get jobs, and then we need to go out to other fields and find whoever we can to be programmers because we can't fulfill the demand, right? So in some sense, the demand is so great that it's far outstripping the supply already. Question?
So I assume these statistics are the U.S. only.
Yeah, this is primarily from I think U.S. or maybe North America. Yeah. The U.S. may be different than the rest of the world. That's absolutely true. But as you saw previously, right, even if you consider offshoring, we still have more jobs in terms of domestic jobs than we do even when we consider jobs going overseas. How? Interestingly, salaries have not, you know, you would think, you know, as an economist, right, supply and demand, salaries should shoot way up.
So maybe that's a problem. Maybe we should just make fewer computer scientists so people get the idea they should pay us.
That's a great idea. So Hal's suggestion was we should have fewer computer scientists until they pay more. I would love it if that were the case. We just need a whole bunch of companies to go along with that concept.
Wasn't it around the time, you know, the Bush administration came in that we got a bunch of new H-1B visas? I mean, hasn't that number expanded exponentially since 2000 as well?
No, so the question was about H-1B visas. So there's a whole separate issue about H-1B visas. And in fact, there's a vast shortage. There's much fewer H-1B visas than the number of people who need them.
Oh, and the other types of visas, the L.
There's like O1 visas. I mean, all across the board, from what I've heard, is there's just a shortage of visas across the board for foreign workers to come to the United States.
Have you done any of the studies on how much maybe kids in college are hearing that we're expanding, so they're not going into the field because they're thinking that need is being fulfilled by people from overseas? It's the same argument, but has anyone looked at the numbers?
Right. So it's whether it's looking at the numbers from overseas. I would say that, I mean, the main numbers that, in terms of overseas jobs, is just how many, I think the bigger worry is how many jobs are going overseas as opposed to how many people are coming to the United States and getting jobs. It could be both. From what I've heard from most parents and students, it tends to be more offshoring than worries about there's too many people coming from overseas and taking all the jobs here, right? The statistics bear out is they need to be coming from overseas and getting jobs here because we don't have enough people here that we're domestically producing to satisfy all those jobs. But even given all the visa quotas that exist, the numbers I've heard is just that there's far too few visas, and the problem is that we're still just struggling to meet this demand.
Visas could also overlap with the green bar because even foreign students coming out of U.S. schools would need visas, so there could be a bit of overlap and false data out there.
Right. So to get the proper statistics, you actually need to do some, conditional estimation there. I haven't done that.
At Google, as in many places, I'm sure there's plenty of people from mathematics and other sciences to fill in that purple bar. To what extent do you think the choice of major is determined by the fact that the perception is that you can study physics and still go into computer science, or study mathematics or statistics or something else, and then easily transition over to computer science because it's somehow easier to pick up?
Right. For most of the students I've talked to, they don't necessarily major in math or physics because they eventually want to be computer scientists. They major in math or physics because that's what they want to do. And I actually had some other statistics that I'm not showing here that show sort of degree production in mathematics and some other fields versus what those fields can absorb. Right. And the numbers are just totally reversed. Basically, the size of the purple bar is about the size of the graduate populations in those fields. And as you can imagine, the people who get degrees in physics who actually end up doing physics, there's cream skimming in that field. They're the best physicists. They're the ones who did very well in graduate studies, and they're the ones who go do physics. And everyone else who was not quite at that same level or for whatever reason decided not to go on to graduate work ends up filling this bar. Right? So I don't think that that's the first order effect is not that they want to fill this bar by going into those fields. It's what happens naturally as a result of the size of that purple bar in those fields.
I'm sure you will come to this later, but one of the phenomena may be that actually it may be better to be a good statistician that learns to program and then fills one of those slots than vice versa, than a computer scientist trying to learn statistics.
Good point.
So
and we'll get to that.
I'm wondering, how these phenomena influence. I mean, a person is maybe not purely a computer scientist, right?
And I think that's the point, is we need to take a broader view of computer science to say that really the traditional notion of computer science needs to be much broader. And by doing that, what we need to think about is for the people who are going into statistics who are eventually going to fill up this bar, making sure that they have at least the proper grounding in computer science to go do it, in addition to all the statistical background they get. And so when we get into the curriculum revision, we're very much kind of in that vein. So let's talk about the curriculum revision. I love it when a question leads into that segue. So at Stanford, our goal is really to educate leaders in computer science. I'll give you a few quick statistics. Our annual degree production here, since we're just talking about degree production, is about 80 bachelors, 125 masters, 35 PhDs per year. And an interesting statistic that Laura Brayfogle just gave me is that there are 550 Stanford grads working at Google. Which if you think about how many students we actually graduate annually versus how long Google has existed as a company, there's a non-trivial percentage of all of our grads that are coming here. Nice work, by the way, I'd say. And our grads want to come here, right? But what our goal really is, right, besides just producing software engineers for Google, is to create leaders to shape the future of the industry, right? In some sense, we want to be producing students that are innovators, entrepreneurs, and leaders in industry, as well as have excellence in research, both going into academia or in industry. Our goal in life is not just to create an army of programmers, right? There's lots of places where lots of programmers are being produced. And what we want to do is produce people that are computer scientists who know how to program, but really are going to be leaders in their field, whatever field they choose to go into. Okay? And that requires a combination of skills. You do need technical fundamentals of programming skills. I by no means want to say, oh, no, let's just get rid of programming. Not at all. We still want to emphasize programming. It's a very fundamental skill as a computer scientist. But you need to also think about creativity and communication with other fields to be successful in understanding where is computer science going to go and how can it impact other fields as well as itself by communicating with others. Okay? So in terms of revising our undergraduate curriculum, just a little bit of background before I get into nitty-gritty. The field has evolved pretty significantly, as you know, in the past 20 years, and generally curriculum has not evolved as quickly, and the field is going to continue to evolve at an accelerating pace. So what we really want to do is we want students to be made explicitly aware of the options in computer science. In some sense, to think about the diversity of areas within a large umbrella of computer science, and to think about the significant role of computing in interdisciplinary different programs, right? It's not trying to fix the curriculum. So to be totally honest, we didn't think our curriculum was broken, right? But that doesn't mean it can't be improved. Moreover, what we want to do is provide a context for computing. Programming is a means to doing something. It's not the end of doing something. There are some people who say, I want to program. I don't care what I program. I just like programming. Just let me program. And that's great. But most of the time when people program something, they want to produce something at the end of it. And that's what they're using programming as a tool for, as the means to reach that end, right? Now, again, I want to emphasize once again, we don't want to discount the importance of software engineering skills. We don't want to water down the curriculum to attract more students. We could increase the number of computer scientists tomorrow by going to our curriculum and saying, oh, you know what? There's too many classes there. Let's just take half of them and throw them away, and the other half, well, we'll just make them really easy. We'll get more computer science majors. That's not what we want to do. We want to have people who are leaders and who have these rigorous skills, but at the same time understand that there's more to computer science than just programming. Okay? What we really want to do, talking about expanding the frontier, is increase the footprint of the field. So here's a two-dimensional projection of the subfields of computer science, just some sampling of the subfields of computer science. And I put a little note here. It's a two-dimensional projection that clearly does not capture the relative importance or organizational nuances of the field. Some topics may be closer to you than they appear on the slide. Okay, so I understand everyone would probably draw this slide differently. And on any given day, I'd probably draw it differently. But here's one way of looking at the footprints of computer science. And what most students get now is they get a program that has some systems in it, it's a little bit of AI depending on where you're at, and some bit of theory, and that's computer science. Right? Traditionally, that's what it's been. And there's all these other areas out here like machine learning and human-computer interaction and security and computational economics, computational biology, that generally you go and do if you want to be a graduate student. Right? Many times, these are the kinds of things that are not available to undergrads, or if they are, they're the one class you take in graphics as part of your undergraduate program. It's the 1 or 2 classes you take in HCI as part of your undergraduate program. It is not a whole program concentrated in that area. And so what we want to do philosophically is basically go from this footprint to thinking about having a track model, where there's still some portion of systems AI in theory someone would get, but a significant part of their program would come outside of the traditional core of what we think of as computer science. And if you think about having more depth here, there's 2 things that come up. One is the total size of that little circle or oval has to remain the same. We can't just say, hey, guess what? We want to increase the field. The number of classes you take just doubled. Right? No, then no one will major in computer science. We need to keep the number of classes the same, essentially, the number of units the same, while allowing this depth. Now, if we can do that, and allow students to choose their depth in a variety of areas, what we end up doing as a result is just making the whole field look bigger. Okay? Because now what's available to you in computer science was not the little thing inside this circle, but you can think of computer science as this whole big pink circle. That's all available to you as an undergraduate now, if we can pull this off the right way. Okay? Now, the total footprint is potentially larger. The core material everyone sees. So this gets to the question of what does it mean to be a computer scientist? What is that common core that everyone's going to share that we call them a computer scientist and give them a computer science degree? That core has to get smaller. It has to get smaller if we want to allow students to take more classes out here. Now, what we've done the last few years is we've actually been expanding the scope of our program by having a bunch of hires in different areas which are looking at computer science and its relation either in different areas like robotics, or Gil Bergerano, for example, as a new faculty member, has a joint appointment in computer science and developmental biology. Okay, so he's actually a professor of biology as well as computer science. And so we have a number of professors we've hired in the department in recent years who really work at these different areas. Scott Clemmer, for example, is in computer science and human-computer interaction. He's also a founding member of our Design Institute at Stanford. Okay? And it kind of goes across the board with a number of different faculty, many of whom I would imagine many of you already know. Okay? So what does the structure of a curriculum look like? There's kind of the high-level picture of where we'd like it to go. What's the structure really look like? So here's the revised curriculum. What we're going to have is a core. This is what everyone's required to take to get a computer science degree. And the core we like to think of as the yin and yang of theory and systems. So it's 3 courses on theory, and I'll tell you a little bit of the details in just a second without going into too much excruciating detail. But it's the notion of mathematical foundations that someone needs to have as a computer scientist, probability theory, which we think of as an increasingly important part of computer science, and data structures and algorithms. On the systems side, it's programming methodology and abstractions, computer organization and systems, so understanding the kind of hardware your program's running on, and principles of systems and networks, so that everyone has to have some idea of how their operating system works and how to do something over a network. They don't need to implement a TCP/IP stack, but they should probably be able to open a socket, for example, and pass some information around between computers. So it's what level you need to know this stuff. Because you can imagine that you could have a whole class on networks, right? That's not what's going to be in here. It's going to be an appropriate amount of networking material to make someone facile to use a network, not to implement a network. Okay? So what do these courses look like? And I've just put a few course numbers up there. How many Stanford alums do we have in the room? A fair number. So I put the course numbers up there in case you were wondering what they are. And some of them are entirely new courses. So Systems 1 is Programming Abstraction Methodology. It's kind of our standard 106 curriculum. Standard sort of stuff like basic data structures, linked lists, binary trees, how to program in C++, recursion, kind of bread and butter, first or second quarter class in computer science. That's followed by Systems 2, which is a reworking of the class that used to be 107. And the philosophy here basically is from the hardware up to your high-level language. So you get a little bit of machine architecture and memory model and data representation, right? You get some elements of compilation. You don't implement a whole compiler, but you should understand what code generation is about and how some intermediate code actually gets generated in your compiler, so you can have a notion of how that's going to sit on top of your machine architecture. And then some basic notions of concurrency, right? This is what's a lock, what's a semaphore, how do I use them in some basic concurrency if there's processes running on my machine, right? So it's from my language basically down to the hardware in one class. And then the third class is what we refer to as Principles of Computer Systems. This is a new class numbered CS 110. If you're kind of old school Stanford, where 110 used to be the old assembly language class, not the same. We're just reusing that number, but a different class. And this is not a class on how to implement an operating system. We still have a class on how to implement an operating system. It's later in the curriculum for people who want to do systems. This is a class on understanding what your operating system is doing and how to use its facilities. So processes and concurrency mechanics, right? What is a context switch? What does it mean to save off that information and switch out some other process? What is thrashing all about? Storage and file management. How do you actually, at a low level, write stuff to disk, read stuff back from disk? And networking and distributed systems, right? Again, not implementing TCP/IP, but being able to be a facile user of TCP/IP or other networking sorts of protocols. Okay? And these are all 1 quarter classes. So basically, it would be a year sequence. Someone doesn't have to do it continuously in a year, but basically a year sequence on the system side. On the theory side, we start off with logical foundations and proof techniques. And this includes kind of all the standard bread and butter discrete math kind of stuff that we expect computer scientists to know, as well as some introduction to formal languages and NP completeness. You might say, wow, I've seen a whole class on NP completeness. This is not 12 of your favorite reductions to SAT. It's understanding that there is a notion of a reduction and perhaps seeing the reduction from SAT to 3-SAT, but you don't have to go and prove 12 different reductions. You do need to know what it means for something to be NP-complete. What are the characteristics of an NP-complete algorithm? What kind of technique would you use if you wanted to prove something that was NP-complete? Okay? So those kinds of things we think we can do in a quarter. Theory 2, this is a brand new class we're going to do, fondly named CS 109, which is Introduction to Probability for Computer Scientists. When I was at Stanford, there was a CS 109, which is my favorite class, and it was a completely different class than this. And I have fun associations with this, because not only is it going to have the same number, but I'm going to be teaching this class. So I look forward to it.
Is calculus a prerequisite?
Yes, calculus is a prerequisite. So there's a number of requirements which are School of Engineering requirements, which I'm not listing up here. That would include a year's worth of calculus, linear algebra, year's worth of physics, for example, actually 2 quarters of physics and then an option for another science class. So science and mathematics are all in there. These are just the ones that are specific to computer science. Great question. So in terms of Introduction to Probability for Computer Scientists, we've traditionally had a class on probability taught in the statistics department that we required our students to take. Perfectly fine class for a statistician, right? It would have a lot of proofs in there, a lot of things where a student would take the class, and a year and a half later they would be required to apply that probability in some class downstream, and they wouldn't remember any of it. And so what we decided was to create a class that has all of that same basics of probability theory. So the first half to 3/4 of the class is probability theory, sort of straight up. And we talk about things like essential theorems, like Bayes' theorem, law of large numbers, central limit theorems. We do proofs. We show inequalities, right? All the kinds of things people have grown to know and love about probability, conditional independence. But we do that all in the context of computer science applications. Multinomial distribution, let's talk about hashing. Markov chain, let's talk about PageRank. Hypothesis testing, let's do data analysis. Right? And then, once we've gotten all the probability theory out of the way, we can actually give an introduction to machine learning as well by showing, for example, how does a recommendation system at Amazon work? How does your spam filter that's doing some kind of Bayesian filtering actually work, and go through the math with students and potentially have them implement that in this class that they're taking at the sophomore level, and hope that that's going to help them remember a bunch of this stuff much better than just doing a few proofs about it. And then the third class is Data Structures and Algorithms, CS 161. This is kind of the classic hardcore data structures class, right? Not the super hardcore graduate class, but this is the kind of class that we would use, the Corman, Leisureson, Revest, and Stein book would show up in this class, right? Algorithmic complexity analysis, various kinds of algorithms on different kinds of structures like trees and heaps and graphs, different approaches like greedy and randomized, dynamic programming, sort of all the things you would expect in a real algorithms class. Okay? And those two sort of things comprise the core. Here's what the prerequisite structure looks like. I won't go into a lot of detail about it, but the basic idea is that we're going to weave together systems and theory. So it's not just you do a bunch of programming and then you do a bunch of theory and the two don't relate to each other. By having a prerequisite structure that's woven together, we can say, hey, finite state machines get talked about here. Guess what? We're going to use finite state automata in it, thinking about your operating system. You did hashing and data structures over there, or you did quicksort. We're going to do its probabilistic analysis over here. Okay, so the two all get weaved together.
This is still a fairly self-centered curriculum. That means it's hard for an outsider to pick a couple of courses and know something reasonable about computer science. And my fear is that computer science is becoming a tool for a lot of people. So 80% of the people who do computer science do something else primarily, but then they need to code. From economists to social scientists to just about everybody. So we need to become something more similar to a math department, where people can take a reasonable small number of courses and have at least the rudiments. This is still hard, don't you think so, for people to just pick a couple of courses and have some basis?
Well, our previous major in terms of depth course in computer science was 15 courses. Right? So we've gone from 15 to 6. So, and these are quarter courses. So this is the kind of thing that in sophomore year, by taking 2 classes per quarter, someone could satisfy this whole thing. We think if you really want less than that, and we had a long debate about what should be in computer science, what is the minimal amount someone could know. And I'll show you some of the tracks that we designed in a second. We actually said, someone doing computational biology, do they need to know about networking if they're doing computational biology? And the consensus overall was yes, that they do, at least at some basic level. So we've gone from 15 to 6. Could we have gone lower? Probably not without, flames erupting in the room. But at least this is a step there. We'll see how this goes, and potentially we might make some more changes down the line.
So this sounds like a great plan. The problem is, my question is, then you need to get a bunch of professors to execute it. And you never get professors to do anything you tell them to do. Right? They each have their own opinion about each course, and maybe some of the interesting relationships won't happen as you plan them.
I'm glad you asked that question. So I'll show you a slide in just a bit to show you who all was involved in this problem. But one of the things we were doing while we were designing these courses was we specifically said, while we're doing the design, is there 1 or 2 at least faculty members who will agree to teach this course and will be on board with this integration? And so we had that designated up front. So as we went through, and they were very closely involved in defining the classes. So our belief is because they were involved in doing the definition, it's not we're just going and handing it to them and say, teach this. They agreed up front to do it and were involved in the integration. But that's a great question because right? You've been through this as to how difficult it actually is to get people to sign up to do it. So I'm happy to say all these courses are staffed for next year, and we're rolling it out. For students who have AP credit or prior programming experience, they can come right into this track. For students who've had no previous experience at all, there's still a funnel, what we refer to as the funnel into the major. It's our current introductory programming class, CS 106A, which actually these days about 800 students take per year. And if you consider that Stanford's each incoming freshman class is only about 600, having 800 students a year take the CS 106A class is a pretty substantial number. And that's not even counting students that go directly into 106B or X, which is also a fairly substantial number. There are some dashed classes up there. Those are classes we might create in the future to stream students into the computer science major by having an introductory programming curriculum, for example, focused on robots or sensors. And for example, MIT, under Hal's direction, has been doing some wonderful things along these lines. So I want to talk more to Hal about how we can potentially borrow some of those ideas for what they're doing. But I think that's exactly the right way to go in terms of broadening the funnel into the rest of the program. And the classes have to be at an appropriate level of difficulty to mature students from not necessarily having done any programming before to being ready to dive into some particular subfield. So that's all the core, which is where a lot of the debate when we were designing this came around. Beyond the core, we have a set of tracks. And the tracks are basically roughly 4 courses. Some are slightly more. And these give students need to complete the requirement for any one track, and it gives them the ability to develop a specialization in some depth. And I'll show you what some of those tracks are, as well as potentially have multidisciplinary options within each track. So here's the initial set of tracks we have. We have 8. Artificial intelligence theory systems, kind of the standard bread and butter. Then human-computer interaction, graphics, information, which I think is a track particularly interesting to Google because it's about the management and application of structured and unstructured data in the large scale. Right? So you can imagine dealing with large-scale data, you have similar issues if you're dealing with a large database, or you're dealing with the human genome, or you're dealing with the web graph. Right? In some sense, all of those share some characteristics of large-scale data problems and data analysis and synthesis that you want to do, and that's what this track is about. Biocomputation. The biocomputation is a real track in computational biology. It is not, here's 1 or 2 classes, are there algorithms for biological sequences, go knock yourself out, now you're a computational biologist. What we decided is that if someone wants to do real biocomputation, they need to have a year of chemistry. They need to have most of a year of biology. They need to be able to have options to take other classes, for example, in the medical school at Stanford. Have them all count toward a computer science degree, which is what we did. So someone can actually do a computer science degree by doing that core set of stuff and then taking a bunch of classes, many of whom are actually in the biology department, and they will count toward computer science, because we really believe that the leaders in computational biology are going to be the ones that are not just algorithmicists, they're the ones who also understand the chemistry and the biology. Unspecialized, so we, at the end of the day, we came up with something where we said, well, what if someone takes a little here and a little there and a little there, and then we said, hey, that's our current program. So we have a track that people who are in flight or who want to do the old program can essentially do it. It's called unspecialized. We specifically chose the word unspecialized to make it unattractive. We did think about making this the generalist track. We decided not to do that. That was a little too generous. We thought about making it the deprecated track. That was a little too negative. And then if someone really can't find anything in all these other tracks, we have an option that they can individually design their own track. And as long as they come up with a coherent program that they get approval for from their advisor, they can do individually designed. So why did we choose tracks? Because it explicitly shows the available options. When someone comes to the course catalog even to look at computer science, they don't see, here's computer science, here's the 15 classes you need to take, all computer scientists do them. What they see is a list of options that looks like that. And it shows classes in things like psychology for human-computer interaction, studio art. Remember our friend studio art? You're doing graphics? Probably a good idea to be able to draw or at least appreciate a good drawing. So we actually let you take art classes and count them toward your graphics program. Okay? And it helps eliminate the image of computer science as just programming, right? It shows the diversity of themes that exist in the field, and it shows you what it's possible to do with a computer science degree besides just thinking of, I get this degree and I program, right? I get this degree and I go make movies, because we have faculty in our department who've won Academy Awards in their graphics work, right? That's what students don't know about, and that's what they need to know. But it still provides the significant programming education to make sure that everyone who comes out from Stanford with a degree in computer science knows how to do this. And that's still important to us. Okay? And it provides organizational infrastructure from our standpoint, right? So from the faculty standpoint, as the field evolves, tracks are modules, right? They are a decomposition of programs, what you did with programs, applied to the curriculum. There's a particular track that's not very popular anymore. It's a function that's not called anymore. You take it out of the program, right? And we can add, modify, and drop things as we need to while maintaining the modular structure of the curriculum. So it makes the curriculum much easier to evolve. Now, you might say, well, beyond the track, what if I just want to take some breadth? I want to take some additional classes. That's perfectly fine. We still have room for students to take a set of electives, and those electives allow them to either take additional breadth classes in computer science, or we have some track-specific electives to allow them to really do more meaningful multidisciplinary work in the particular track they've chosen. And, question?
So this starts to sound a lot like symbolic systems. Have you guys talked to them at all about subsuming their program possibly, or at least coordinating with them so that, for example, symbolic systems HCI and symbolic systems AI are almost exactly what you're describing here.
Right. So
just with some non-CS classes in the specialization.
Yeah, that's a good question, because symbolic systems is a popular program. We've talked to the symbolic systems program directors about the changes we're making. The biggest difference right now between incorporating symbolic systems as a track of what we're doing is that we're in the School of Engineering, so we still have all the School of Engineering math and science requirements. Symbolic systems in humanities and science, so they don't have that. So that's an issue we need to resolve. Track and elective structure, and I don't think we want to subsume in the long run. I think symbolic systems is a great program, and we don't want to try to fold it into computer science. We just want to make sure that it's clear to students which is the right program for them. So tracks and elective structure, I won't belabor this point. I'll just go through just this bottom point very quickly, which is that in the track there's multidisciplinary options. So if you do the biocomputation track, you can take classes in genomics and dynamic models in biology, which is actually a class taught, and I think in our med school and our biology department. Those count toward computer science. If you're doing graphics, studio art, you draw pictures. It counts toward your graphics program. And you might wonder, weren't people up in arms? No, in fact, the people who were pushing for this requirement were the graphics faculty, because they said there's too many people who do computer graphics who don't know what a good drawing is, and they should actually understand that. Or things like understanding the psychology of vision. If you understand how someone perceives an image, that tells you where you should be putting your computational cycles in terms of rendering that image. And HCI, classes like needs finding, psychology of perception, cognition, to think about how do people really understand and interact with some software artifact, or what do they really need that's outside of just the realm of software. Okay? And the idea is hopefully we can have some appeal to non-traditional students. So we wouldn't be nearly as worried if rather than this was being biology and statistics, was computational biology and machine learning. Right? So we want to bring some of those students over in some sense to the computer science side. Last but not least, we still require a capstone class. This is a senior project that everyone's required to do. just like we've had before. That doesn't change. So to get to Alon's point, were people really on board with this? So I'll show you who in our department was actually involved. We had the curriculum committee and then a whole bunch of people beyond the committee. We had the vast majority of the department who was substantially involved in this. And by substantially involved, I don't mean an email, right? That gets in the many additional faculty who sent emails. These are faculty who showed up at meetings, who helped design curriculum, who had real conversations about this stuff, or agreed to teach classes. And one interesting thing about this is there's actually lots of ties to Google. So I just highlighted in red all the folks in here who have some kind of tie to Google, either through funding or who've worked here or advised one of the founders. But as the case may be, there's lots of ties with the department. So I'll briefly go over issues. There's a bunch of issues we've considered. I already talked about this. The curriculum isn't broken. Why fix it? Students won't know what to take. They don't need to know what to take right away because there's a common core, and then we can provide advising to help them out. But more importantly, will students know what track to take, right? If everyone's taking these general computer science classes, how do they know what artificial intelligence is about? Well, we work a little bit of AI or a little bit of theory into some of those introductory core classes, but each track also has a gateway course, which is kind of like the survey of that idea. So if you do AI, there's the Intro to AI class. You take that class. If you like it, you go on and you do that track. If you don't like it, you can count that course as an elective, so there's no penalty for trying out different areas because you have these electives that you need to fulfill anyway. And if you manage to sample 4 or 5 of the gateway courses, this is kind of the dilettante track, and you manage to say, oh, there's none of these that I actually like, what am I going to do? Well, you're going to graduate under the unspecialized track because the unspecialized track is basically all the gateway courses. Okay? Additional issues, what if very few students take a particular track? That's information gathering, right? If no one's taking a particular track, that tells us something about student interest in the field. And we have a master's program, and some of the master's program concentrations are small, but they're still available, and they give us information about where students are going. This is the big one that I think is the most controversial issue. Won't students take fewer systems courses and potentially have weaker programming skills? Okay? There's 2 things to say about this. One is there's still, as was mentioned, there's still a substantial amount of programming in the curriculum. So students will still be well prepared if they want to go into a programming job. But not all students want to take a high-intensity programming job, right? Students who do will take the systems track. And guess what? They'll be even better prepared in systems than our current program prepares them now. And for those of you who've gone through the current program, you know it's a pretty good systems program. And to give you data along those lines, 47%, or about half of our master students, actually choose the systems track. We think with undergrads it'll be the same, but there's a large number who will choose to do other tracks as well. So broader context, just finishing up quickly. There is a broader context for this. The IEEE and ACM have a Computing Curricula 2001 report. The track model fits neatly in that. There was a workshop a couple years back called Integrative Computing Research and Education, which was held at Stanford. I'll just highlight a few people who may be around. There's Ellen, who's sitting right there. She was at that workshop. Dave Patterson, who was president of the ACM at the time, always rubbed his head for good luck. Stuart Regis, who's actually funded by a Google grant, and there was me. And a bunch of other people you know, like there's Eric Roberts, there's Dan Garcia from Berkeley, so a bunch of folks from West Coast universities. And some of the recommendations that ICER made was that we need to change the popular image of computing, encourage curricular experimentation, make sure introductory students recognize the breadth of the field, and strengthen interdisciplinary connections. And we think we're hitting all those with the curriculum revision. Many peer institutions are moving in the same direction for similar reasons without even publicizing this curriculum. So basically, we just kind of improved it internally. This is one of the first public forums. We're talking about this outside of Stanford. We've already had folks from University of Washington, University of Maryland, and Cornell contact us about this program to see what portions of it might be interesting to them. And we want to push it out more broadly. We have some other ideas under consideration. One would, for example, be a seminar to freshmen that's great ideas in computer science. Just a 1-unit seminar that tells them about different areas by showcasing faculty and industry speakers. I may, at some point, hit some of you up for that kind of speaking engagement. And it's also a venue to have women and minority speakers come and say, you know what, computer science is not all about white men who wear glasses. It's really a diverse field, and we need to build that diversity going forward further. And also talk about these issues like career paths and offshoring to really give them the facts so they can understand it. So broadening the initiative, just to wrap up, this need for curricular reinvigoration is not unique to Stanford. As I mentioned, many schools are grappling with the same issues and have the same kind of drops in enrollment. Stanford, I think, has the opportunity to have a continued leadership role in education. We've done it in the past. We have the opportunity to do it again because we're well placed to make the changes and experiment and actively engage the computer science community with results, writing papers, talking to people in industry, right? That's why part of the reason for coming to talk to you is to get feedback on this kind of thing, and material generation, writing books, etc. So the end of the day is really to engage both from the academic side and the industry side. If there are things we're doing well that you like, that'd be good to know. If there's things where you think we missed the mark, it's important to get your feedback and incorporate that into the curriculum going forward. Because in the end, the pipeline is something that affects us all. It's not just that the NASDAQ goes up and students choose to go to computer science, but 20 years from now, it'll be whether or not students chose to go into computer science now that's going to affect what the NASDAQ looks like. It's a bidirectional relationship. And so we can all have an impact on it. So thanks very much for your time.